According to the 2020 National Electrical Code, specifically NEC Section 408.3a, you cannot connect 3 panels with a triple lug on each phase within 10 feet of the load side of the main 600 amp disconnect using 3/0 copper conductors. NEC Section 408.3 establishes requirements for the supply of panel boards. It stipulates that panel boards must be supplied by individual branch circuits. In your scenario, each of the 3 panels would be classified as a branch circuit. NEC Section 408.4b further clarifies how branch circuits should be connected to panel boards. It specifically states that branch circuits supplying panel boards are required to originate from a single circuit breaker or fuse. Therefore, each of the 3 branch circuits serving the panels must originate from a dedicated circuit breaker. Given the 600 amp service, these 3 branch circuits would necessitate originating from a single 600 amp circuit breaker. The use of a triple lug to connect the 3 panels to the 600 amp disconnect would not comply with the stipulations outlined in NEC Sections 408.3a and 408.4b. Using a triple lug creates a connection that bypasses the requirement for individual branch circuit originating from a single overcurrent protection device. In practical terms, the NEC aims to ensure that each panel board is fed by a properly protected branch circuit. This design philosophy is intended to enhance electrical safety and prevent overload. The code emphasizes that each panel receives power through a circuit breaker or fuse that is appropriately sized for the panel's load. By mandating individual branch circuits, the NEC seeks to maintain the integrity of the electrical distribution system and safeguard against potential hazards. Let's delve into a more detailed explanation of why using a triple lug is non-compliant. The fundamental issue is that the triple lug creates a parallel connection from the 600 amp disconnect to the 3 200 amp panels. This configuration circumvents the code's requirement for each panel to have its own dedicated overcurrent protection device at the source. When a fault or overload occurs in one of the 200 amp panels, the 600 amp disconnect may not trip quickly enough to protect the 3/0 copper conductors feeding that panel. The 3/0 copper conductors are sized to handle 200 amps, and a fault current exceeding that level could cause them to overheat and potentially lead to a fire. In contrast, if each 200 amp panel were fed by its own 200 amp circuit breaker connected to the 600 amp disconnect, a fault in one panel would cause only that panel's 200 amp breaker to trip. This would isolate the fault and prevent it from affecting the other panels or the main 600 amp disconnect. The NEC prioritizes this level of selective coordination to ensure that only the affected portion of the electrical system is de-energized during a fault. Now, let's consider the implications of NEC Section 408.3 regarding individual branch circuits. This section highlights the importance of treating each panel board as a separate load. By requiring individual branch circuits, the code reinforces the concept that each panel should be independently protected and controlled. This approach allows for better load management and ensures that the electrical system can handle fluctuations in demand without compromising safety. Furthermore, NEC Section 408.4b reinforces the need for a single point of overcurrent protection for each branch circuit supplying a panel board. This requirement stems from the understanding that each circuit should be protected by a device that is specifically designed to interrupt the flow of current in the event of an overload or short circuit. By mandating a single circuit breaker or fuse, the code aims to simplify the protection scheme and reduce the likelihood of coordination issues between multiple overcurrent devices. To summarize, using a triple lug to connect the 3 200 amp panels to the 600 amp disconnect violates the fundamental principles of the NEC regarding branch circuit protection and panel board supply. The code requires each panel to be fed by an individual branch circuit originating from a single circuit breaker or fuse. This design ensures that each panel is properly protected against overloads and short circuits and that the electrical system as a whole operates safely and reliably. So, instead of considering the triple lug approach, you should explore alternative wiring methods that comply with the NEC. One option would be to install 3 separate 200 amp circuit breakers in the 600 amp disconnect and feed each panel with its own set of conductors. This approach would satisfy the requirements of NEC Sections 408.30 and 408.4b and ensure that each panel is properly protected. Another possibility might involve using a distribution block or power distribution unit to split the 600 amp service into 3 separate 200 amp feeds. However, it is crucial to ensure that any such device is properly listed and labeled for the intended application and that it complies with all applicable NEC requirements. In any case, it is advisable to consult with a qualified electrical engineer or inspector to determine the most appropriate and code-compliant wiring method for your specific installation. They can provide guidance on conductor sizing, overcurrent protection, and other relevant aspects of the electrical design. In addition to the specific NEC sections discussed above, it is also important to consider other applicable requirements such as those related to conductor ampacity, overcurrent protection device ratings, and grounding and bonding. The NEC is a comprehensive document that covers a wide range of electrical installation practices, and it is essential to be familiar with all of the relevant requirements to ensure a safe and compliant installation. Before making any decisions about the electrical design, take the time to carefully review the NEC and consult with qualified professionals. This will help you avoid costly mistakes and ensure that the electrical system is installed in accordance with the highest standards of safety and quality. Remember that the NEC is not simply a set of rules to be followed blindly. It is a comprehensive framework that reflects the accumulated knowledge and experience of electrical engineers, contractors, and safety experts. By understanding the underlying principles behind the code requirements, you can make informed decisions and create an electrical installation that is both safe and reliable. Now let's further clarify the concept of branch circuits as they relate to panel boards. A branch circuit, by definition, is the circuit conductors between the final overcurrent device protecting the circuit and the outlet or load served. In the context of panel boards, the branch circuit extends from the circuit breaker or fuse within the panel board to the individual loads connected to that panel board, such as lighting fixtures, receptacles, and appliances. The NEC distinguishes between different types of branch circuits, such as general-purpose branch circuits, appliance branch circuits, and individual branch circuits. Each type of branch circuit has specific requirements regarding conductor sizing, overcurrent protection, and the types of loads that can be connected to it. When designing an electrical system, it is crucial to carefully consider the types of loads that will be served by each branch circuit and to select the appropriate conductors and overcurrent protection devices accordingly. In the case of panel boards, each branch circuit must be properly sized to carry the anticipated load and must be protected by a circuit breaker or fuse that is rated to interrupt the flow of current in the event of an overload or short circuit. Furthermore, the NEC places restrictions on the number of outlets that can be connected to a single branch circuit, particularly in dwelling units. These restrictions are intended to prevent overloading of the circuit and to ensure that the electrical system can safely handle the anticipated demand. In commercial and industrial settings, the number of outlets per branch circuit may be less restrictive, but it is still important to carefully consider the load requirements and to ensure that the circuit is adequately sized. Now, let's delve into the concept of overcurrent protection and its importance in electrical safety. Overcurrent protection is the practice of interrupting the flow of current in an electrical circuit when it exceeds the safe operating limits of the conductors or equipment. Overcurrent can occur due to a variety of factors, such as short circuits, ground faults, and overloads. Short circuits are caused by unintended connections between conductors of different polarities, such as a hot wire and a neutral wire. Ground faults occur when a hot wire comes into contact with a grounded surface, such as a metal enclosure or a water pipe. Overloads occur when the current in a circuit exceeds the ampacity of the conductors, typically due to excessive loads being connected to the circuit. Overcurrent protection is essential for preventing damage to electrical equipment and for reducing the risk of electrical fires. The NEC requires that all electrical circuits be protected by overcurrent devices, such as circuit breakers and fuses. Circuit breakers are devices that automatically interrupt the flow of current when it exceeds a predetermined level. They are typically resettable and can be used to restore power to the circuit after the fault has been cleared. Fuses are one-time use devices that melt and interrupt the flow of current when it exceeds their rated value. They must be replaced after they have been blown. The selection of the appropriate overcurrent protection device is critical for ensuring the safety and reliability of the electrical system. The device must be sized to protect the conductors from overcurrent, but must not be so sensitive that it trips unnecessarily due to normal fluctuations in load. The NEC provides detailed guidelines for selecting the appropriate overcurrent protection devices for different types of circuits and equipment. In addition to circuit breakers and fuses, other types of overcurrent protection devices are available, such as ground fault circuit interrupters (GFCIs) and arc fault circuit interrupters (FCIs). GFCIs are designed to protect people from electric shock by detecting small imbalances in current between the hot and neutral conductors. They are required in locations where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor areas. FCIs are designed to protect against electrical fires by detecting arc faults, which are dangerous electrical discharges that can occur due to damaged or deteriorated wiring. They are required in many areas of dwelling units, such as bedrooms and living rooms. In summary, overcurrent protection is a critical aspect of electrical safety. It is essential to select the appropriate overcurrent protection devices for each circuit and to ensure that they are properly installed and maintained. By following the guidelines in the NEC, you can create an electrical system that is safe, reliable, and compliant with all applicable codes and standards.